With conjugated dienes, we're typically going to see dienes with 2 or more double bonds joined by 1 single bond. Conjugated dienes are sometimes also called 1,3 dienes, and that's because 1,3 dienes only have a sigma bond separating the 2 double bonds. There's no placeholder carbon in between those 2 systems. 1,3-butadiene is the simplest conjugated diene, and it is used a lot in later chemistry. There are 3 stereoisomers possible for 1,3-dienes with alkyl groups bonded to each end of the carbon. Take, for example, 2,4-hexadiene. You can have trans-trans 1,3-diene, where both of the double bonds are in a trans stereo configuration. You can have cis-cis 1,3-diene, where both of the double bonds are cis. Or you can have cis-trans 1,3-diene, where one double bond is cis and the second is trans. When we have conjugated dienes, there's 2 possible conformations that result from the rotation around the carbon-carbon bond that joins the 2 double bonds together. We can have a cis conformation, where both of the double bonds are on the same side based on rotation. Or we're going to have S-trans conformation, where the double bonds are separate on either side of where the sigma bond is. Stereoisomers are discrete molecules, whereas conformations interconvert. We can easily convert from S-cis conformation to S-trans conformation by simply rotating the sigma bond in our molecule. But in order to go from a cis-cis isomer to a trans-trans isomer, we have to break and reform the double bonds. Therefore, sometimes it's going to appear very easily for you to find the desired compound that we're using for Diels-Alder cycloadditions. Sometimes, though, you'll have to sit there and draw these out to make sure you're drawing them in the right formation. Features of conjugated dienes. There are 4 features that distinguish conjugated dienes from isolated dienes. There's a short CC single bond joining the 2 double bonds. If we compare the length of a typical sigma bond is 153 picometers, whereas the single bond between 2 double bonds is 148 picometers, which means it's shorter. And that usually indicates that we have some form of movement between those bonds with the conjugation. Conjugated dienes are more stable than similar isolated dienes. Some reactions of conjugated dienes are different from reactions of isolated double bonds. And conjugated dienes absorb longer wavelengths of ultraviolet light. These are all the common features of conjugated dienes. One of the things that we'll see is the %S character versus bond length is going to be substantially different for a conjugated system. The observed bond distances can be explained by looking at hybridization. Each carbon atom in 1,3-butadiene is sp2 hybridized. So the central carbon-carbon single bond is formed by the overlap of two sp2 hybridized orbitals, rather than the sp3 hybridized orbitals used to make the carbon-carbon bond in ethane. Because we have sp2 hybridized carbons, we have a smaller distance between those atoms in a conjugated system. Carbon-carbon sigma bond length in 1,3-butadiene is an example that we're going to take a look at. A resonance argument can also be used to explain the shorter carbon-carbon sigma bond length. If we take a look at the resonance structure for B and C, we'll see that in both those cases there is a double bond between carbons 2 and 3, where we had a sigma bond in the first structure A. Because there's that double bond in B and C between carbons 2 and 3, that's going to pull those two atoms closer together, which is going to result in a shorter bond, a shorter sigma bond for carbons 2 and 3. Well, we've already said that the conjugated dienes are more stable. But just how much more stable are they? If we take and compare the values for hydrogenation for the double bonds versus isolated double bonds, so conjugated versus isolated, we'll see that in 1,4-pentadiene, when we add two equivalents of hydrogen with palladium on carbon, it costs us negative 255 kilojoules per mole of energy. The conjugated system, what we see with the conjugated 1,3-pentadiene is that the hydrogenation only takes 226 kilojoules of energy, which is more stable. Less energy is required to hydrogenate the 1,3-pentadiene over the 1,4-pentadiene. That makes, therefore, a conjugated diene is more stable by 7 kilocalories per mole of energy.